Welcome to Brain Vision.
Okay, so for this question, we can set out the energy balance equation, which is E dot N equal to E dot R. If we expand it, we have Q dot plus M dot H1 is equal to M dot H2. Q dot here is the rate of heat transferred into the air. M dot is the mass flow rate for the air. H1 is the initial enthalpy for the air. And H2 is the final enthalpy for the air. If we do some arrangement here, we have Q dot is equal to M dot times H2 minus H1. So we know the rate of heat transfer into the air can be equal to the power input from the electrical heater, which can be expressed as a potential multiplied by the currents. So therefore, we have Vi is equal to M dot times H2 minus H1. And we know H2 minus H1 can be expressed as Cp times T2 minus T1, since the pressure is constant in this case. So we can use the specific heat of the air at constant pressure, which is Cp here, multiplied by the final temperature minus the initial temperature of the air. And this will give us Vi is equal to M dot times Cp times T2 minus T1. And then we have I is equal to M dot times Cp, and then times T2 minus T1 over V. So we know the mass flow rate can be equal to the initial density of air times the volume flow rates at the inlet, which can be also equal to P1 over RT1 times V1 dot. So P1 here is the inlet pressure for the air, R is the gas constant for the air, and T1 is the initial temperature in the Kelvin form, okay? Because gas constant is having units Kelvin. And then V1 dot here is the volume flow rate. So eventually we have I is equal to P1 times V1 dot times Cp times T2 minus T1 over RT1V. So we know the initial pressure or the inlet pressure is given as 100 kilopascal. And the final temperature is 30 degrees Celsius. The gas constant for the air is 0.287 kilojoule per kilogram times Kelvin. The initial temperature is 15 degrees Celsius, which is 288 Kelvin. And we know the specific heat at the constant pressure for the air is equal to 1.005 kilojoule per kilogram times degrees Celsius. And the potential is given as 110 volts, and the volume flow rate is given as 0.3 meter cube per second. So now let's plug in back to the equation to determine the currents. So the current should be equal to P1V1, which is 100 kilopascal times 0.3 meter cube per second, and then multiplied by Cp, which is 1.005 kilojoule per kilogram times degrees Celsius, and then times the changing temperature, which is 30 degrees Celsius minus 15 degrees Celsius, and then over RT1V, which is 0.287 kilojoule per kilogram times Kelvin, and then times the initial temperature at Kelvin form, which is 288 Kelvin, and then multiplied by the potential, which is 110 volts. And this will give us the currents is about 0.04974 kiloampere. If we convert it to ampere, it's about 49.74 ampere. And this is the answer for this question.